To most humans, the definition of time is the relationship between the Earth and the Sun. For example, a day is 24 hours, and that's the time it takes for Earth to rotate around its axis. Now, when we look on a more advanced scale, we have the year. Now, the year is 365 Earth days, and that's just how much time it takes for Earth to revolve around the Sun. Now, as you can see, time, to most humans, is just defined as the relationship between the Earth and the Sun. Now, we can derive the second just by using the definition of a day. So a day, as mentioned, is 24 hours. Now, 1 hour is going to be a unit of time. Now, we can break that 1 hour into 60 minutes. So 1 minute is also another unit of time. 1 minute is equal to 60 seconds. And we get another unit of time, which is just a second. Now, we can keep on going till we get very infinitesimal units of time. But the most relevant right now is the second. Now, the second, as mentioned, is just 1 over 86,400th of a day. So 86,400 seconds is equal to 1 day itself. Now, when we look in chemistry, we have a more complicated definition. So in chemistry, the definition of a second is 9,192,631,770 cycles of the microwave line of cesium-133 with a wavelength of 3.26 centimeters. So as you can see, 9,192,631,770 cycles of the microwave line of cesium-133 is the definition of a second in the SI unit system. Now, this definition of a second is very useful because we won't have much discrepancies when we're creating an invention and replicating it in another place. Now, to learn more about the SI unit of time and space, mass, and energy, and to learn more about mixtures, solutions, homogeneous materials, heterogeneous materials, continue watching to the end of this video. Hi everyone, welcome back to my channel, and today I'm going to be talking about general chemistry. So as we talked previously, we have the second, and the second is defined to be 9,192,631,770 cycles of the microwave line of cesium-133 with a wavelength of 3.26 centimeters. Now this is the definition of a second. Now, what's the reason to create a definition of a second that's so complicated, than rather using the definition of a second in relation to the Earth and the Sun? Now, the main reason comes from the lack of discrepancies. Now, the lack of discrepancies is good right now because we have a fair definition of a second itself, because this is actually a good definition. But if we have a more loose definition, so a definition that isn't much specific, there could be major discrepancies between an object and its replica. So if we have an object, an invention, and its replica, we wanted to have the same mechanisms and hence we wanted to have the same outputs. But if we have discrepancies and we have loose definitions of how much, let's just say, a pound or a second is, then they're going to be loosely operated, and we can take different quantities of time and, for example, even weight, for example, to even operate on that invention. And if we take a different amount of time than compared to the other person, then we're going to get different outputs. And even if we just do a minor discrepancy, a minor loose definition, this could cause drastic outputs that we don't want to happen. So it's important to have a proper and specific definition of time, weight, and pretty much anything that we can define. So this is why we have a more complicated definition of time. And the reason we have a complicated definition of the second here is because when we're looking at chemical reactions, maybe even nuclear physics, and multiple other things in chemistry, having a more precise definition can lead us to more precise results. And this is why we define the second as 9,192,631,770 cycles of the microwave line of cesium-133 with a wavelength of 3.26 centimeters. Okay, now notice this is the SI unit of time. The SI unit of time is the second. We define the second to be this over here. So this is the definition of a second. Now, the SI unit of force is going to be the Newton. Now, a Newton is pretty simple. It's just what the force is needed to accelerate 1 kilogram by 1 meter per second squared. Now, we can write this 1 meter per second squared as 1 meter, or we can just write 1 meter per second squared. So we want to accelerate 1 kilogram by 1 meter per second squared, and if we do that, we'll get a Newton. So that's how much force is required to accelerate 1 kilogram by 1 meter per second squared. So that's essentially what Newton is, and that's what we're going to be using when we're talking about forces. Next, we have the joule. Now, the joule is also a very important definition. Now, the joule is the unit of energy which the work is done by 1 Newton in 1 meter. So how much work is done by 1 Newton in 1 meter? And the work that is done by 1 Newton in 1 meter is going to be considered the joule. Okay, so that's the definition of a joule. Now we have the unit of mass. Now the unit of mass is the kilogram, and it's a platinum iridium alloy in Paris. Now this is another important thing about the discrepancies of an object and its replica. So we have mass over here, and the SI unit for mass is the kilogram, not the pound, but the kilogram. Now the SI unit of mass is the kilogram, and it's a platinum iridium alloy kept in Paris. Now, it's a specific type of material that is kept and is supposed to weigh exactly 1 kilogram, and we can use that as a reference weight when comparing it to other measurements. And this also deals with the purpose of wanting a lack of discrepancy. If we have a lack of discrepancy, an object and an object replicas will give the same output, which is what we want. If it gives different outputs, potentially it can be beneficial, but majority of the times it's not beneficial, and it can create drastic outputs which we don't want. So this is why we need to give a proper definition of anything that we have, any measurements that we have in chemistry, physics, engineering, and so on and so forth. So a platinum iridium alloy, which is kept in Paris, is supposed to weigh 1 kilogram. And since that's supposed to weigh 1 kilogram, we can use that as a reference weight when comparing it to other things. Okay, so this is the SI units which we're talking about today. So we talked about the second, which is not defined using the Earth and its relationship to the Sun. It's defined to be 9,192,631,770 cycles of the microwave line of cesium-133 with a wavelength of 3.26 centimeters. Now, an SI unit of force is the Newton, which is the force to accelerate 1 kilogram by 1 meter per second squared. Now, the force that's required to accelerate 1 kilogram by 1 meter per second squared is going to be the Newton. Now, the joule is the unit of energy, which is the work done by 1 Newton in 1 meter. And the unit of mass is kilogram. And it's a platinum iridium alloy kept in Paris. Now, as you can see over here, we can kind of define some of the definitions here, like a Newton, which is over here, or the joule, which is over here, by using the other units itself. For example, a joule is based from a Newton and a meter, and a Newton is based by a meter and a second. So since a Newton is based off a meter and a second, and a joule is based off a Newton and a meter, we can obviously see that they have an intricate relationship between each other. So the SI units can often be created from the other units itself. So you don't need an extra unit which is not in the SI unit system, which is pretty cool. Okay. Now let's talk about mixtures and solutions. So in our previous video, we talked about mixtures and solutions. Now, we talked about mixtures and solutions on a slight level. We talked about them by talking about homogeneous and heterogeneous definitions. The definition of a homogeneous material is that it has the same properties throughout, and the heterogeneous material is that it has different properties throughout. Now, a mixture and solution is primarily defined upon these two definitions. So if we talk about those, we pretty much talk about the main things about mixtures and solutions. Okay, so let's talk about a solution. So a solution is primarily just when we combine two items together and we can't really see the difference. So moreover, it's homogeneous. Now this came when we're talking about pure substances. Now the definition of a pure substance is that it has to have reasonably definite chemical composition and it must be a homogeneous species of matter. If it satisfies these two properties, then it's considered a pure substance. Now we can essentially craft this definition of a solution by just primarily taking out one of the main rules, especially the first one. we don't have to have reasonably definite chemical composition. So if we don't have a reasonably definite chemical composition, then we're just going to have a homogeneous species of matter. So solution is just a homogeneous species of matter that has the same properties throughout, and it's pretty much a mixture. Like, you can't identify that we have two different things that has two different properties. It's just two things or two or more things combined that act like they have the same properties. Kind of like statistical mechanics in physics, where we're just trying to understand the system we're studying as a whole, rather than just looking at more of the individual particles. So as you can see, we have the solution to be an ordinary solution is homogeneous, and this means it has to have the same properties throughout. And notice a solution is a type of mixture. It's a homogeneous mixture. Now, thanks for the book General Chemistry by Linus Pauling for giving all the definitions we're talking about in this video. Okay, so now continuing. So as I just said, a solution is just an ordinary solution that is homogeneous, and this means it has the same properties throughout. And a solution is a type of mixture. So the solution itself is pretty much just a combination of two things that are homogeneous, or two or more things. Now, over here we said a solution is a type of mixture. It's a homogeneous mixture. Now, what does this imply? And this implies that a mixture doesn't always have to be homogeneous, because if it always has to be homogeneous, then we can say that a solution and a mixture are synonyms of each other. But that's not the case, because a mixture is not a synonym to the solution. Okay, so over here we have the definition of a mixture. So a mixture is a homogeneous material that does not fall under the category of pure substance. So that's one definition of the mixture. And two, it's a heterogeneous aggregate of two or more substances. Okay, and this is just something else about the second, which is 1/86,400 of the mean solar day. Okay, so these are the two definitions in which the mixture operates on. Now let's decode these definitions properly step by step. So the mixture is a homogeneous material that does not fall under the category of a pure substance. Now, it's a homogeneous material that does not fall under the category of a pure substance. That's what a mixture is. Now, this, as you can see, is primarily the definition of a solution. So a mixture can either be a solution or is a heterogeneous aggregate of two or more substances. Now, a homogeneous material is a material that has the same properties throughout, and it does not fall under the category of a pure substance. So that means it doesn't have reasonably definite chemical composition. So a solution is primarily a homogeneous material that does not have reasonably definite chemical composition, and it's just a combination of two or more things. That's what a solution is. Now, we have the heterogeneous aggregate of two or more substances. Now, heterogeneous means that it doesn't have the same properties throughout. It has some different properties throughout. That's what heterogeneous means. So if it has the same properties throughout, that's called homogeneous. But heterogeneous is the opposite of that. So an aggregate is when we're combining two different things together, of two or more substances. So if we're combining two or more things together that are totally different and do not obey the same properties throughout, that can also be called a mixture. So if we have two things that are that primarily don't mix well together, so on a scale that we can observe with our eyes, maybe they might look like they can mix together, but when we look at a more chemical scale, molecular scale, they can't mix together well. So they can't mix together well, but they are made of two or more substances and they're heterogeneous. That is also the definition of a mixture. So a mixture can either be a solution or a heterogeneous aggregate of two or more substances. Okay, so now that we've talked about a mixture and a solution, and we've talked about the time, which we define as a second, so that's the SI unit, which is 9,192,631,770 cycles of the microwave line of cesium-133 with the wavelength of 3.26 centimeters, the SI unit of force, which is Newton, the SI unit of energy, which is joule, and we talked about the SI unit of mass, which is the kilogram. We can make this video to an end. If you like this video and if you like this channel, please subscribe to learn more. Thank you.